Bayes' theorem is one of the most important concepts in probability theory and statistics, named after Reverend Thomas Bayes. This theorem provides a mathematical framework for updating our beliefs or hypotheses when we receive new evidence. The formula shows how prior knowledge can be combined with new data to produce more accurate conclusions. Now, let's examine each component of Bayes' theorem. P of A given B is the posterior probability. This is what we want to find. P of B given A is the likelihood, the probability of observing our evidence if our hypothesis is true. P of A is the prior probability, our initial belief before seeing evidence. And P of B is the evidence probability, the total probability of observing the evidence under all possible scenarios. Let's work through a classic medical testing example. Suppose a rare disease affects only 1% of the population. We have a test that correctly identifies 95% of sick people as positive and correctly identifies 90% of healthy people as negative. If you test positive, what's the probability you actually have the disease? Using Bayes' theorem, we first calculate the total probability of testing positive, then apply the formula. Surprisingly, even with a positive test, there's only an 8.8% chance of actually having the disease. This counterintuitive result demonstrates the importance of considering base rates. This tree diagram visualizes our medical test example with 0 people. Starting with 100 diseased individuals and 900 healthy ones, we apply the test accuracy rates. The test correctly identifies 95 diseased people as positive, but also incorrectly identifies 990 healthy people as positive. When someone tests positive, they're in a group of 85 people, but only 95 actually have the disease. This visual representation clearly shows why the probability is only 8.8%, despite the test's high accuracy. Welcome to our exploration of Bayes' theorem. This fundamental concept in probability theory provides a mathematical framework for updating our beliefs when we encounter new evidence. Named after Reverend Thomas Bayes, this theorem shows us how to calculate conditional probabilities and has revolutionized fields from medicine to machine learning. Let's break down each component of Bayes' theorem. The prior probability represents our initial belief before seeing any evidence. The likelihood tells us how probable our evidence would be if our hypothesis were true. The evidence is the total probability of observing what we saw. Finally, the posterior is our updated belief after incorporating the new evidence. This framework gives us a systematic way to update our understanding. Let's work through a classic medical example that demonstrates the counterintuitive nature of conditional probability. Imagine a rare disease that affects only 1% of the population. We have a test that's 95% accurate. It correctly identifies the disease 95% of the time and correctly rules it out 95% of the time. If you test positive, what are the chances you actually have the disease? Most people guess around 95%, but the answer is surprising. Let's solve this step by step. First, we need to find the total probability of testing positive. This includes true positives from people with the disease and false positives from healthy people. Out of 0 people, 100 have the disease and 95 of them test positive. But 900 are healthy, and 5% of them, that's 495 people, also test positive. So out of 590 total positive tests, only 95 are from people who actually have the disease. That's just 16.1%. The rarity of the disease makes false positives much more common than true positives. Bayes' theorem has countless applications across many fields. In medicine, it helps doctors interpret test results. In machine learning, it's the foundation of many algorithms. Email systems use it to filter spam, and scientists use it to update theories based on new data. The key insight is that base rates matter enormously. When dealing with rare events, even highly accurate tests can produce surprising results. This theorem provides a mathematical framework for rational decision-making under uncertainty, helping us avoid common cognitive biases and make better informed decisions.